Topic Notes 8.1 Plate Tectonics. If you haven't noticed, the Earth is always changing. This is evident in everything from mountain ranges, volcanoes, earthquakes, landslides, you name it. This is a picture of the Grand Tetons, which is a spectacular mountain range in Wyoming. So here are your big main ideas for today. The Earth's crust is made up of large tectonic plates that interact with each other, continually changing the surface of the planet. Then you have all of the nuts and bolts of your individual learning goals. Remember, these are all reflected in the learning scales on your topic focus sheets. Before we get too far along, I want you to take a look at this picture of the Earth. For most of human existence, this picture was not available. People could only experience the world that was literally right in front of them. The perspective that we have now on our planet is very special and hard-earned. It allows us to see large-scale changes as they occur and look for evidence of past changes. As a result, we now have a better concept of the Earth as a very dynamic place. Now I'm going to tell the story of the discoveries that led us to our modern theory of plate tectonics. We'll begin with a German scientist named Alfred Wegener in 1912. After studying clues spread throughout the globe, Wegener eventually came up with his theory of continental drift. This theory states that the continents have moved horizontally to their current locations. Now, this was a radical idea at the time, when most conventional thoughts were that the Earth was very static and unchanging. Now, this concept of a static, unchanging Earth seems almost laughable now, just because we know what we're looking at. But at the time, this was a new concept, and a lot of people were upset by it. Now, Wegener had a lot of evidence. Here listed are some of the key components. First of all, he looked at all of the different continents and the way they were shaped, and many of them looked like they fit together. Not perfectly, mind you, but they looked very similar. For example, if you take South America and Africa and put them together, they sort of fit cradled into each other. Another piece of evidence was fossil distribution. There were many examples throughout the world where fossil populations could be found on two different continents. As the continents stood today, those populations would have been separated by whole oceans. How could that possibly happen? How could they intermingle and breed and keep genetic flow across an entire ocean? It was probably unlikely. There were also rock and mineral distributions. Now, most specific types of rocks and minerals form under similar conditions. So when you see areas of one continent that have similar rock and mineral features as areas in an adjacent continent, the concept of them forming when they were both together seems very more likely. We also have climate evidence. For example, glacial scarring on the land that occurs as a glacier is forming and retreating oftentimes can be linked together in land masses that once were connected. Now, no one piece of evidence that we just talked about really conveys that these continents moved. But when you start to put all of the pieces of evidence together, it starts to tell a convincing story. Wegener believed that all land masses at one point in time were connected together in a supercontinent called Pangaea. Pangaea literally means all land. And this formed over 300 million years ago. You can see a drawing of this on the bottom left. Now, by about 250 to 260 years ago, Pangaea began to break up, and that's where these continents begin to separate out into what we would consider their modern positions. Now, this all makes logical sense. However, Wegener didn't have a solid mechanism for these continents to move. And at the end of the day, because he lacked a good mechanism to really make people believe that these continents could move, his theories were generally dismissed at the time. Now, as we move a little bit farther along in time, we come to the era of World War II. There was a growing need to detect submarines. This led to the development of sonar. Now, sonar stands for sound, navigation, and ranging. Basically, it uses sound very much like dolphins use echolocation to locate objects in the water. Not only did this allow military vessels to try and find submarines, it also allowed scientists to start to map the deep ocean floor. Now, at the time, people really didn't know much about the ocean floor. They didn't really even know how deep a lot of the ocean was. So back in World War II, Harry Hess was a geologist, but also a naval officer. While crisscrossing the oceans, he not only utilized sonar to locate submarines, but also started to track ocean geology data using sonar. He eventually published what he found in History of Ocean Basins in 1962. What Hess and other geologists found was that the ocean floor was not flat. It was incredibly diverse in all sorts of structures. Some of the most massive mountain ranges on the planet were literally under the ocean. This new data would actually lead to the modern theory of plate tectonics. In a nutshell, it provided the data that Alfred Wegener never had because technology was not available during his time. This is generally an important concept in science because as we develop new technologies and new ways to collect data, we can go back at our earlier ideas and refine them. Now we're going to get into the modern theory of plate tectonics, but before we do need to understand a few terms. The Earth is broken up into layers. Now we are going to concern ourselves with mostly the surface layers. The lithosphere is that outermost layer of the Earth's crust made up of the various different tectonic plates. The asthenosphere is this nearly liquid layer made of the uppermost part of the mantle. The asthenosphere is basically what the lithosphere is riding on. Now the mantle exists between the core and the lithosphere. You'll often see the mantle described as molten rock in textbooks. However, that's a little misleading. The mantle is mostly solid, but is pliable, kind of like a flowing plastic, especially at plate boundaries. And so now we come to the grand view of the entire planet. The lithosphere is literally broken up into about 8 large plates and a bunch of smaller ones. These plates float independently on the asthenosphere. Continents are embedded in the plates, but they are not the entire plates themselves. This was actually the clarity needed by Alfred Wegener to fully understand all his observations and ideas. It really took us uncovering the geology of the ocean basins to really understand that the continents themselves were not floating around independently. They were part of these larger plates. Other than that, however, Alfred Wegener's observations and evidence all still apply to the modern theory of plate tectonics. And so plate interactions cause all of the geology that we see on our planet: mountain ranges, mid-ocean ridges, and deep-sea trenches. In fact, the deep-sea trench you see there on the bottom right is actually the Marianas Trench, which is the deepest in the world. It goes down about 37,000 feet. Now, of course, with new data and new concepts, we have additional evidence to support plate tectonics. The first is seafloor spreading. One of the key features we uncovered as we mapped the ocean floor were these gigantic long mountain ranges called mid-ocean ridges. These ridges form what we call divergent boundaries, where the two plates are moving apart. As they move apart, molten material makes its way to the surface, creating these mountain ranges and new seafloor along the way. There is actually one place where a mid-ocean ridge comes up on land, and that is in Iceland. The pictures you see there on the bottom left and the center show you this mid-ocean ridge up on land. But most of the time, this is underwater in very deep water, very dark environments. However, the molten material, the pillow lava that you see on the right, is actually a product of that volcanism. We also have evidence coming from the magnetic polarity reversals we see embedded in the rock strata. Now, hopefully you may know that the Earth has a magnetic field. It's actually a really important component to our existence because it helps shield us from radiation from the sun. But what most people don't know is that our current magnetic north and south poles were not always where they are today. In fact, throughout geologic history, our poles have actually reversed over and over again. Now, the major type of rock we found on the ocean floor is basalt. And basalt has an iron material called magnetite in it. And that magnetite aligns itself to the magnetic field at the time of its formation. That means as new molten material is emerging from the divergent boundary at the mid-ocean ridge, it's going to cool and solidify oriented to the magnetic field that currently exists on the planet. Now that newly formed rock will begin to spread away from the divergent boundary as the two plates pull apart. The Earth's magnetic field will then reverse again. Now the new molten material coming out at the spreading center will align to the new reversed pattern. This continues to happen over a long period of time, creating a banding pattern on the ocean floor of various reversals. Earth's magnetic field reverses on average every 250,000 years. We can also look at the age of the seafloor, and very obviously, the rock nearer the mid-ocean ridge, where the molten material is forming new seafloor, has younger ages compared to farther away from those ridges. The image here actually shows you that. The red actually indicates younger rock, whereas the cooler colors are older rock. Of course, plate boundaries are characterized by these interactions they have. This is a map of earthquakes and volcanoes, and you'll notice that they align very well to the plate boundaries. Now we're going to take a look at the three different types of plate boundaries. We'll start with the convergent boundary, where the plates move towards each other. There are actually three different types of convergent boundaries we can have, where two oceanic plates come together, where an ocean plate and a continental plate come together, and where two continental plates ram into each other. Either way, you're going to get earthquakes and you're going to get volcanoes. And in the case of the continent-continent collision, you're going to get a massive mountain range. An example of this, of course, is the Himalayas, as the Indian plate is actually running into the Eurasian plate. An example of a oceanic plate and a continental plate coming together would be South America and the Nazca Plate in the Pacific Ocean. That's what's forming the Andes Mountains. And of course, there's a deep trench also associated with that particular zone, right off the coast of South America. That trench is where the oceanic plate is subducting under the continental plate. This typically happens because oceanic crust tends to be denser than continental crust. When you have two oceanic crusts coming together, generally whatever the denser of the two oceanic crusts will actually subduct. You get a deep trench. You also get an island arc based on the volcanoes that are going to appear along the subduction zone. You can find examples of this in the Caribbean, the island of Japan, and throughout the Pacific. Then, of course, we have divergent plate boundaries. Now, I'm not going to spend too much time talking about this because we've just been talking about them. This is where you have the mid-ocean ridge, you have a spreading center, and you're forming new seafloor. The last type of interaction is a transform boundary. This is where two plates are moving in anti-parallel directions, otherwise known as they're sliding past each other. This can cause some major earthquakes, and the San Andreas Fault in California is a big example of this. Now I'm going to briefly talk about some of the mechanisms, what causes the plates to move. The first idea is what we call mantle convection. This is where heat from Earth's core is transferred through the mantle through density currents, just like you would a pot of boiling water. And these convection cell currents actually cause friction to the bottom of the lithospheric plates, causing them to move in one direction or another. There's also what we call ridge push. Now, this happens at mid-ocean ridges as the mountain ranges sort of build up on either side of the divergent boundary. The mass, the weight of them, is pushing down on the lithosphere, and that causes a force. We also have a slab pull. As a piece of the lithospheric plate is subducting under another, there is a suction force that pulls it along. The truth is, scientists are still studying this. We don't know all the answers, and we are not 100% certain in all the forces involved. These are the best ideas we have so far that are backed up by evidence and data. However, there is much more to learn, so if you have any budding geologists out there, we need your help. Alright, it is time to turn it back over to you. How does our knowledge of plate tectonics affect where and how we build our cities and towns, especially anywhere around the ocean? So, that's what we got for you today. Until next time, keep thinking.